Okay, so last hour we have already learned that if we use RF power supply with the sinusoidal output form, okay, RF power supply with sinusoidal output form, and the surface of the top electrode or the surface of the RF top electrode will become most time negative charge and with very small time positive charge. Okay. And the average potential of the RF hot electrode will become negatively charged with a bias voltage, and this is called DC offset. DC offset, or sometimes called DC bias. So the surface of the top electrode is automatically charged to negative bias, and this is called self bias, negative self bias. Okay. And in the first slide here shows if we use DC plasma and place a piece of insulating material inside the DC plasma, the surface will be charged to a floating potential, negatively charged. Okay. The surface is negatively charged to the floating potential, and usually the floating potential is only a few tenths of volt, Right? In a capacitive type RF discharge, if you place an insulator on the RF hot electrode, the surface potential can be much higher. For example, 1,000 or 2,000 volts, minus 1,000 or minus 2,000 volts. Okay, so you can use this kind of the cell bias to undergo different types of the plasma reaction. Okay, and in our class, one chapter is the sputtering. So if you use this type of the discharge, you can run RF sputtering, because the sputtering process requires high energy cation, and negative sheath voltage or negative bias voltage can accelerate accelerate cation to very high energy. So this is called self-bias. And in 1963, Porter and Kino conduct an experiment to measure the self-bias of the RF insulating electrode. So these two figures explain how they measure the self-bias voltage. Okay, so it might take some time to realize these figures. Okay, so at the first step, one can generate a plasma. And in their experiment, they use DC power to generate plasma. DC plasma. Okay, and then you can place a probe, electrical probe. Okay. And in our class, there is also one chapter of the electrical probe. Okay. So we can use electrical probe to measure the physical property of plasma. Okay. So once you place the electron probe into the plasma, you can pass current or apply voltage to the electrical probe. Okay. So the electrical probe, when they contact with plasma, the electrical charge can transfer to plasma, or the charge in plasma can transfer to electrical probe. and form a closed loop of circuit. A closed loop of circuit. Okay. So in that circuit, we can use one DC power supply to connect to the probe. One end of the DC power supply connect probe, and the other end of the power supply connect ground. Okay. And it will form a closed loop circuit. Closed loop circuit, because when the probe touch plasma, plasma is also a part of the circuit. Right? And plasma in a plasma system, the plasma system, there is always some place is connected to ground. Connected ground. Okay. So the probe itself and plasma and the power supply can also form a closed circuit. So if you apply voltage to the probe, and then you can measure the current flowing through the probe. So the first curve in the left figure here is the IV curve. Okay, so the vertical axis here is the current flowing through the electrical probe. And the horizontal axis in this part is applied voltage. Applied voltage. Okay. And at this point, the electrical current equals to 0 amp. So this is zero net current point. Zero net current point. And since the probe is not exposed to plasma, so that the probe surface is bombarded by both electrons and ions. Electron is negative charge, ion is positive charge in the plasma. So that the probe collects electron currents and ion currents, but the net current equals to 0 amp. It means the probe is at floating potential. So at this point, the probe is at floating potential. Okay, because the current flowing through the probe equals to 0 amp. So at the first step, you can set up your system so that the probe really is 0 amp. So it means it's at floating condition, floating potential. And then you can use another power supply to pass an RF signal here, to pass RF through the electrical probe. So the lower figure here, this horizontal axis is the applied voltage of the RF signal. So right here. So here is the RF signal voltage, and the horizontal axis is time. So actually you pass a sinusoidal RF signal to probe. So at this period, half cycle, the probe is biased positively, and this half cycle, the probe is biased negatively. Right? So again, when the probe is biased positively, the probe will collect extra electrons from plasma. From plasma. And then when the probe is biased negatively, the probe will collect extra ion currents. So the third curve in this figure, here, the vertical axis is the current collecting by the probe after one passes the RF signal, and the horizontal axis is time. So for this half cycle, when the probe is biased positively, the probe collects electron current. And the electron current right here is much larger than the ion current in another half cycle. So this curve this part is excess electron current, and this part is ion current. Okay. So this is at the beginning when you pass RF signal to a floating probe. And if you keep passing the RF signal for a while, so eventually the probe will bias automatically. Okay. So because in this cycle we already know the probe collect the extra electrons compared to the ions now in one cycle. So the probe will become negative charge after you passing the RF signal. Right. At the beginning, the probe is at floating potential, so there is no net charge. Positive charge and negative charge are equal. After you passing the RF signal through the probe collects more electrons than ions, so that the probe becomes negatively charged, and the potential of the probe will shift to a negative bias potential. Okay. So on the right figure, the bottom curve shows that the potential of the probe shifts down, right? And this value is the DC offset. DC shift or DC offset, so that the probe becomes biased negatively. And the last curve here shows the current, electron current and ion current collected by the probe after the probe is biased negatively or self-biased negatively. So again, at the last, if we calculate the area of the curve in this half cycle and in another half cycle, we can find out the area here, the electron current, and the area here, the ion or electrical charge and ion charge become equal. Okay. So at this condition, the probe is biased negatively, and this bias or the DC shift equals to the negative self-bias of the floating material in the plasma, okay, in the plasma system. Okay. So Gardner and Kinnock proved by the experiment that in a system, if the surface of the electron or surface of a piece of substrate is connected to an iron power supply, the surface will automatically bias to negative charge. Okay. And in industry, people like to use high power supply to generate plasma, compared to DC power supply. The high power supply is more efficient in generate plasma. So high discharge is more efficient than its DC counterpart in promoting ionization and the sustaining of the discharge. Okay. So in the first chapter in the nature of plasma, we have already known that there are two patching curves. One is the striking. So from neutral gas state to plasma state, we need to strike plasma. And after the plasma is generated, we need to keep a continuous plasma discharge. So that part is sustaining. Okay. So here, the ionization, at the beginning the ionization, and then the sustaining of the discharge. The RF power is more efficient than the DC power. Okay. And the frequency of RF power can be a few megahertz or less than megahertz. So for example, for the low frequency RF power supply, the frequency is about 100 kilohertz. And for the high frequency RF power supply, the frequency could be 40 megahertz or a little bit higher. So there are different types of RF frequency people use for the RF power supply. And for low frequency RF power supply, the behavior of the RF discharge is similar to the double-ended DC discharge. Okay. And for high frequency RF discharge, the function of the cell bias start working. Now then one can generate plasma easily. And in industry, the typical frequency of the RF power supply is 13.56 megahertz. So if you use the RF power supply with such a frequency, and if you control the gas pressure at 1 milliton, you can generate plasma easily. Okay. And now the chapter of the nature of plasma, the patching curve gave us one very important technical information. For DC discharge, the pressure times the distance or the length of cathode layer thickness, P times D, is about 1 centimeter tall. So at that condition, plasma can be generated at lower voltage. If the P times D value is smaller or larger than about 1 centimeter tall, the voltage required for the DC plasma discharge become very high. So it is not easy to generate a DC plasma. Okay. So if you use 1 milliton of the gas pressure, 1 milliton, right? 1 milliton of gas pressure, and from the patching curve, the optimized PD value is around 1 centimeter tall. So it means if the pressure is 1 milliton, you need a system with 1,000 centimeter length. 1,000 centimeter length. 1,000. 10 meters. Such a large DC system to generate plasma. But in RF system, even the pressure is only 1 milliton, you can generate plasma easily with a system with a distance between cathode and anode around 2 centimeters. So compared to a DC system, you need a system with 10 meter of the distance between cathode and anode to generate plasma at 1 milliton of gas pressure. Okay. So for the 13.56 megahertz high power supply, you can generate plasma at low pressure easily. But for the low frequency RF discharge, the discharge is more like a DC discharge. So their behaviors are a little bit different. Okay. And in order to generate plasma, the most important equation or most important reaction is electron impact ionization. Electron impact ionization. So in a plasma system, if the electron temperature is high, then the plasma can be generated easily. Okay. So electron temperature, or in other words, electron energy, is very important in the plasma system. Okay. So this part of this equation help us to calculate the electron energy. So the first equation is the sinusoidal wave of the RF field, or the AC field. RF is the high frequency AC. Okay. So the electrical field E, in the first equation, equals to E0 cosine omega t. And E0 is the amplitude of electrical field. So the electrical field equals to the voltage, the voltage difference divided by distance. So you can consider the voltage across cathode and anode divided by distance between cathode and anode. Okay, so at the beginning you can consider it like this way. Okay, so in a RF discharge system, they applied a voltage. Follow the first equation, E equals to E0 cosine omega t. And the electrical field can accelerate electron in the opposite direction. Electrical field. Okay. So the acceleration of the electron follows the Newton's equation. F equals to ma. F is the force, electrical force, equals to ma. M is the mass. Right here is the mass of electron. A is acceleration. So in this equation, x with two small dots here is actually representing the acceleration. And ma here. And the right side of this equation is the force. The charge times electrical field equals to the electrical force. So the force work upon the electron equals to the energy here, ma here, F equals to ma. M times the mass times the acceleration, not the energy, okay, ma. And the third equation shows the velocity of electron. Velocity. So the velocity of electron equals to the integration of accelerating voltage. Acceleration times time, delta t. So you can integrate the second equation and get the velocity, right? So then the third equation, x with one dot here, means the velocity. Velocity of electron equals to minus E times E0. The first, a small e, is the charge of electron, right? And the capital E0 is the amplitude of electrical field. So in this equation, the velocity equals to E times E sub 0 divided by the mass of electron and the frequency. Omega is the frequency of the ion power supply. And then sine omega t. Okay. And the energy of the electron equals to 1/2 of the me times V squared. Right. This is the kinetic energy of electron inside plasma. And since the mass of the electron is fixed, a fixed value, so that the electron energy is proportional to the square of velocity, electron velocity. And electron velocity is proportional to electrical field, and inversely proportional to high frequency. Okay. Inversely proportional to high frequency. So that the energy of electrons depends on the electrical field and high frequency. So if the frequency is small, the electron energy inside the plasma will be large. So if you use 100 kilohertz of RF power supply to generate plasma, you will get a plasma with inside the plasma the electrons with very high energy compared to the RF power supply of 13.56 megahertz. Okay. So then for the low frequency RF power supply, you will generate a plasma with very high electron energy. And for the high frequency of RF power supply, you can generate plasma with a medium electron energy. Okay. And the fourth question here X is the displacement of electron under the RF field. So under the RF field, electron will travel back and forth, because the direction of RF field change with time. So the electron will travel back and forth. And the maximum distance of the electron can travel is here, X. So this table shows the calculation of the amplitude of the electron, and the velocity of the electron, and the energy of the electrons inside an RF system. And the RF power supply is with 13.56 megahertz. Right? RF 13.56 megahertz. So this table from this table you can see if the applied electrical field equals to 10 volts per centimeter. If the applied electric field is 10 volts per centimeter, and from the last slide we can calculate the electron amplitude, and then travel back and forth or oscillate. When they oscillate, the distance the electron can travel is around 2.42 centimeter. Okay. And from the velocity, and also we can know that if the electrical field is 10 volts per centimeter, the velocity of electron can reach around 2 times 10 to 8 centimeter per second. And the energy of electron reached 11.3 eV. Okay, so for only such small electrical field, the electrons inside the RF plasma, can reach 11.3 EV energy. Okay, and from the previous lecture notes, we know that for the atom plasma, the ionization energy of atom is around 15.7 electron volt. 15.7. And the excitation for atom is around 11.5 eV. Okay, so for this condition, if the electron energy is 11.3 eV, it's close to the excitation energy of atom gas. And if the electrical field of the plasma system is few tenths of volt per centimeter, the energy of electron can be increased more than 15.7 electron volt. Okay, so for an RF system with only the few tenths of volts per centimeter of electrical field, one can ionize argon easily. Okay. So from this analysis, the ionization energy of argon is 15.7 eV. Okay. So it can be easily ionized, and then plasma can be generated. Okay. And there are other other functions of the plasma or other contributions of the RF field to the electron energy. Okay. So sometimes the electrons undergo elastic collision with other atoms and change their direction when they travel. Okay. So if the moment of the change of direction by elastic collision with other atom meet with the change of direction of RF field, electrons can be accelerated continuously, so that the energy of the electron can be higher than the energy listed in this table. Okay. And sometimes we want to increase the time for the accelerating of the electron. We can also use the magnetic field. So combine the RF electrical field and fixed magnetic field. Okay. And the electron might reach a resonance condition, so that the energy acquired from the electrical field can be very, very high. So even a very weak electrical field, one can generate RF plasma easily if the electron reach the resonance condition. Okay. In the next two slides. Okay. In the Chapman's book, he also explained other effects of RF, which can increase the energy of electron and enhance ionization. Okay. So the first part is the multi-packing effect. So in the multi-packing effect, we can just look at the surface of chamber wall or surface of electron. Okay. Because in the plasma system, there are charged particles like electrons and ions. This charged particle will travel along any direction, and some of these charged particles will collide with chamber wall or the surface of electron. So this collision can generate secondary electron from chamber wall or from the electron surface. Okay. And if we place a piece of material inside plasma, the surface and the plasma, between the surface of the material and the main volume of the plasma, there is a thin layer, which is called sheath, plasma sheath. Okay. And the surface potential and the plasma potential are different. The difference is the sheath potential. Okay. So the plasma sheath can also work on the charged particle. So the electrons, secondary electrons coming out from surface of chamber wall or surface of the electrode can be accelerated by plasma sheath. Accelerated by plasma sheath. So the sheath will push the electron away from the surface and back into the plasma volume. Okay. But in RF system, the sheath will also change with time. So the sheath is not a fixed condition. So actually the sheath will change with time because the electrical field, the direction of electrical field also change with time. So the sheath will move back and forth, back and forth, back and forth. Okay. So such sheath might cause enough or efficient ionization of the test because this moving sheath can increase the energy of electron. If the motion of electron reach a resonance effect, resonance state. Okay. And for such a multi-packing effect, the condition is F times D greater than 70 megahertz per centimeter. F is the frequency of the RF power supply, and D is the spacing of electrons. Okay. And here is the sentence, last sentence said here. So actually, the peak-to-peak voltage needs to be higher or as high as 1,000 volt to promote the multi-packing effect. Okay. Okay. And this slide shows another advantage of RF discharge. It is named the self-writing. Okay. And this part is from another textbook, Lieberman's book. Okay. So you can read the Lieberman's book to realize the complete story of the self-writing. Okay. So in this video, we can see the shadow part is the surface of the chamber wall or surface of electron. Okay. So the electrical field is along the horizontal direction. In this slide, electrical field is flowing along the horizontal direction. And here, B0 is magnetic field. So the magnetic field pointing up. Okay. So the magnetic field is perpendicular to electrical field in this system. Okay. So if an electron travel toward the surface of the electron or the surface of chamber wall with an initial velocity of u, with the initial velocity of u, and because the system is equipped with magnetic field, so that the path of electron will follow a circular motion, because the existence of magnetic field. So here, this part is an electron coming toward the surface of the electron with the velocity of u, and then non-necessary surface, the edge of the plasma sheath, edge of plasma sheath, and then when the electron collided with the plasma sheath, a moving sheath, the electron will be reflected back. So if the velocity of the plasma sheath, the sheath edge move back and forth, like this way, the velocity is u sub es. Okay? So when the electron collides with the moving sheath, it will be reflected back, and the velocity of the electron will become minus u plus 2 times u es. Okay. So this is basic momentum conservation, momentum transfer. Okay. So that the electron velocity change, and then the direction of the electron traveling also change. At the beginning, the electron will be reflected back, so the electron will travel in a direction perpendicular to the sheath edge. But again, the moving charged particle, when they experience magnetic field, the path will become a circular direction, so that the electron will travel, follow this path. And then at this point, it is collide with the moving sheath again, Okay, so the electron will gain energy again. So at the beginning, the electron is with the energy of minus u plus 2 times ues, and after the second collision, the electron energy becomes minus u plus 4 times ues. So this reaction will happen several times, and the energy of electron or the velocity of electron can be increased so to a certain value. And since the energy of the electron equals to 1/2 of the mass of the electron times the square of the velocity of the electron, so by the working of the moving sheath, the energy of the electron will keep increasing. Okay. And this effect is named the self-righting effect, because the sheath oscillates back and forth in the RF field. So the sheath itself can push electron back, so that the energy or the velocity of the electron will increase by the sheath. Okay. So this is another effect, and you can read the paragraph in Lippmann's book. Okay. Okay. Any questions?